All right. Oh, I need to press this. Okay. Thank you very much, and thank you very much for having me here. So just a heads up, there's pretty much no Poisson geometry here. I very much apologize. There's some geometry and some mathematical physics. So this is a report on a project with Olga Chekeres, Andrei Losev, and Donald Youmans, and well, here's the arXiv kind of place, and I should really emphasize Andrei Losev here. This is his ideas that we were trying to process. So, okay, so the plan is roughly like that. So I want to talk about what is Fukaya-Morse category, and I want to try to sell its well, an enhancement, and an enhancement is a particular model for automorphisms of objects in this category. So, and then I wanted to discuss two, well, sort of physicsy viewpoints on it. So one physicsy viewpoint, well, has different names, well, second quantization approach or effective field theory approach. So that will be the situation where we are looking at some gauge theory or topological gauge theory, and then we're interested in some particular effective action for it. And well, effective action is computed by, well, some path integral, which is ultimately about some Feynman diagrams, and Feynman diagrams will be precisely the same sort of Morse trees as we are counting in this category. So they just become realized as Feynman diagrams computing an effective action. So and this also corresponds to sort of why we started to think about it, which is, so this Fukaya-Morse story for us was a metaphor for a completely different situation where we were supposed to be counting tropical curves. And well, tropical curves are also kind of Feynman diagrams for some field theory. Okay. So, and there are actually many analogies with that situation. So, and kind of the second physicsy picture that I wanted to present is not about gauge theory, it's about topological quantum mechanics. Well, H stands for higher topological quantum mechanics, so higher in some sense. So, which lives not on intervals as kind of usual quantum mechanics, but on also on trees, and well, I'll explain what I mean there. So then the space where the A-infinity category lives becomes the target. So in the picture one, X is the source, or kind of manifold where the field theory lives, and in the picture two, it becomes a target. Okay, so right, I want to talk a little bit about, well, this Fukaya-Morse A-infinity category. So this is based on two papers. So a paper by Fukaya from '93, I think it's maybe lecture notes, and kind of more details and kind of analytical details were filled in Fukaya O paper from '97. And well, another very influential paper, which we were kind of where we found a lot of things, was a paper of Kantsevich and Soibelman from 2000. So, and well, many things that I will be speaking about here kind of were in that paper. Okay, so the objects in this category are just a collection of functions on a Riemannian manifold X. So just some collection of smooth functions, and we want them to be sufficiently generic. And what we want is that the differences of different functions are Morse functions, or Morse-Smale actually. So, okay, so just immediately making sort of a parallel with a usual Fukaya category of Lagrangians in a symplectic manifold. So here we should be concentrating on the symplectic manifold of form T star X, a tangent bundle, and we should be looking at projectable exact Lagrangians, so graph of the form graph of the differential of a function. So those should be exactly the same functions. So, and well, I would like to put a parameter epsilon here, so to scale those Lagrangians so that they're nearly, well, very close to the zero section. And I'll say why I need this parameter in a second. So, okay, so morphisms on the right side are intersection points of two Lagrangians, or I'm allowed to take a formal linear combination of intersection points with some integer coefficients. On the right side, morphisms are, well, Morse chains of a difference fa minus fb. So morphisms between two functions are critical points of the difference. And again, I'm allowed to take formal linear combinations with integer coefficients. Okay, and well, actually, these intersection points, they precisely project to such critical points. Now, the most interesting story is the composition maps, or well, higher composition maps, which I actually denote M in both cases. So let's say that I have a sequence of Lagrangians, L1, L2, ... Ln, and I have kind of a morphism, which is an intersection point between L1 and L2, a morphism between L2 and L3, another intersection point, and so on, up to Pn minus 1n, an intersection point between like the last pair of Lagrangians. Then the composition map is the sum over intersection points of the first and the last Lagrangians with certain integer coefficients, and the integer coefficients, they're counting, well, certain holomorphic disks, so holomorphic maps from a standard disk to T star X. With so that well, the arcs on the boundary of the source disk, they go on their image lies in the respective Lagrangians, and sort of points between those arcs, they go to the intersection points that we fixed. Okay, so it's the count of holomorphic disks, or rather, there's a modular space of holomorphic disks, and if its dimension is 0, then we're counting the number of points in it. If the dimension is non-zero, then well, this term vanishes. Okay, and the corresponding counterpart on the kind of on the right is, sorry, this is left. On the left is, okay, we have a critical point of difference f1 minus f2, critical point of f2 minus f3, and so on. So, and then we are the composition map. The composition gives you the sum over critical points of the difference of 1 minus fn with some coefficients, and the coefficients here are counts of, well, Morse trees. So let's say an example. So I have my well, let's say n is equals 3. So I have I'm looking at the critical point p12 and a gradient trajectory of f1 minus f2 going out of it. Then I'm looking at the critical point of P23 of F2 minus F3 and the gradient trajectory of F3 minus F2 or F2 minus F3 going out of it. And well, I want them to merge together at some point, and then to follow up as a gradient trajectory of F1 minus F2, and I want this all to end at some critical point. Sorry, that's 3. Some critical point of f1 minus f3. So we're counting this Morse trees. So there are univariant vertices which are located at critical points, and well, there are edges that are bicolored. So which are following gradient trajectories of differences of my functions. And yes, please.
So, yeah, sorry, I have a question. Is it like kind of obvious that they will generically merge like you draw?
So, well, there is kind of a dimension of the moduli space of such trees. So, and it depends on what? On the indices, on the Morse indices of this point. So under some balancing condition and under some genericity condition, or transversality condition, they will merge.
So you're basically saying sometimes the picture is like you're drawing.
Yes, exactly. So yeah, exactly. Or sometimes there will be, I don't know, some positive dimensional space, and then we are not counting those. We want 0 dimensional.
I was just more worried that they just miss each other.
Yes, that can also happen. So yeah, so we are interested in the so generally that would correspond to, I don't know, negative expected dimension.
Okay. Okay.
So we are interested in a situation when there's a balancing condition between the indices. When it's 0 dimensional, there still can be some, I don't know, integer number, for instance, 0, or 0 or some, or a positive integer of such graphs. Okay. So yeah, so maybe kind of more general pictures. Yeah, the graphs, the trees can be, of course, more complicated, but well, they have a root somewhere. And in the original paper, I think these trees were presented well as maps of ribbon trees sitting inside a disk. So you're imagining a tree sitting inside a disk, so it's kind of automatically coming with some ribbon structure. So you're coloring the regions, for instance, here, and you're mapping this tree that sits inside the disk into your manifold so that, well, these edges go along gradient trajectories. That's another way to imagine these pictures. Okay, so now I promised that epsilon is important. So yeah, actually, the point is that if I think of this epsilon and I look at the holomorphic disks and I project the holomorphic disks from T star x to x, well, I'll have something two-dimensional in x, but as I take epsilon smaller and smaller and smaller, this shadow of a disk will become thinner and thinner and thinner, and in the end, it will sort of approach this graph. It will be just slightly thickened version of this graph. Okay, so in this sense, it is sort of the picture on the right. On the left is a degeneration or epsilon to 0 limit, and also projection to x of the picture on the right. Okay. So the enhancement that sort of I'm trying to sell here, and well, and actually I don't know, maybe people have thought about it. I'm not quite sure, so couldn't find it. So let's say is the following enhancements to consider the space of morphisms from an object to itself to be the singular or smooth singular chains of x. So on the Fukaya side, we would say that morphisms from a Lagrangian and itself, those should be the singular chains of, well, on the Lagrangian itself. Here we're kind of operating in the shadow, and the shadow of the Lagrangian is x itself. Okay, so now with this convention that automorphisms are singular chains, the composition maps, so I need to say something more about what they are. So I'm taking kind of a bunch of chains, Z1, 1, dot, 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 Z1, I don't know, K1, so a bunch of chains on X. Then I take some morphism from F1 to F2, which is a critical point of the difference, then another bunch of chains, then another critical point, and so on. So a critical point and a bunch of chains. So the first index tells me sort of I'm considering this chain as a morphism of, as an automorphism of which object. Geometrically, it's just a chain. So then the composition map applied to these inputs is, okay, it's a sum over critical points of F1 minus Fn with, again, integer coefficients. And the integer coefficients now count Morse trees with extra conditions that they should pass through a given set of chains. So let's say I have a bunch of chains here. So as morphisms from F1 to F1, then I should count Morse trees where this kind of blue line, or which is actually a part of my graph. So edges that contain the blue color, they should pass through my blue chains, and then I might have like a collection of red chains, and my sort of edges of the Morse graph that contain the red color should pass through the red chains, and so on. And here I can also have some green chains. Okay, so it's counting Morse graphs with extra conditions, Morse trees with extra conditions. Okay, so unary compositions here are differentials. So it follows from the definition above that the unary map applied to a critical point is just Morse differential applied to that critical point. So, and something that we need to sort of add to the picture is that the composition applied to a single chain is the just geometric boundary of the chain. Now, if I have two chains as sort of automorphisms of some object, then I can compose them, and I get it's also sort of an injection of data. So I appoint this composition to be the intersection product of chains. And if I have more than two chains, then the composition is 0. This is the convention. Okay. So now the A-infinity relations here, so they're saying that what you have is not, strictly speaking, a category, so the composition is not associative, but it's almost associative. So what happens is, well, let's say that I have a collection of morphisms, so that x1 is a morphism from some object, well, fa1 to, well, fa2, which is the same as b1 in these notations. X2 is a morphism from fa2 to fa3, and so on. The last one is a morphism from ap to fap plus 1. So then it's a composable kind of chain of morphisms. And each of them is either a critical point or a chain. So it's a chain if the consecutive A's are the same, or it's a critical point if they're different. Then it's the critical point of the difference of functions. Okay, so I have this collection of morphisms. Then the infinity relation tells me the following. So let's write the sequence. Let's choose some subsequence and apply composition to the subsequence, and then apply the composition to the entire thing. So I've chosen some subsequence of morphisms. I applied the composition, and then I applied M to everything. So, and sum over all ways to choose a subsequence should be 0. So that's the A-infinity relation. And well, of course, there are some signs here. I just didn't want to write them explicitly. So, or kind of another style of drawing these pictures is like that. So I have, well, a bunch of inputs, x1 through xp, and then I'm choosing a sub collection. I apply the composition to them and plug the input as the, well, corresponding entry of the next composition. So those are quadratic relations on composition maps. So you can also draw kind of the objects in this picture, while sort of drawing this as a ribbon graph. So that would be object 1, object 2, object 3, and so on. So if you draw it as a ribbon graph, then you are remembering the objects as sort of borders, decorations of borders. Okay, so here's an example of an A-infinity relation using chains. So let's say that my manifold is a sphere, and I have just 2 functions in the game, and their difference is the sort of is a height function in the sphere, which is embedded in, I don't know, in R3 as this heart-shaped sphere. So I want f to be the, well, this z direction, so the height function. So then there are 4 critical points, so 2 critical points of index 2, 1 of index 1, and 1 of index 0. So let's look at the A-infinity relation, which uses as inputs, well, this critical point as the first input, and, well, this chain, let me make it very thick, as the second input. Right, so then my A-infinity relation tells me the following. So, okay, the following terms. So I have 2 inputs to play with, and I can put the inner composition on either of the inputs or on both. So this should be 0 with, okay, maybe with some signs. So let's actually calculate what's going on here. So the first term, well, this is just, okay, the same. The first term, so this is the Morse differential of P. So Morse differential of P is R, because there's, well, a unique rigid gradient trajectory here. So this is the critical point R. And then what is the whole thing? So I want gradient trajectories of the height function, starting at r, ending at some critical point, and passing through z. Well, there's only such a gradient trajectory if the target critical point is s, and then there's exactly one. So this one. So that means that this first bracket is s. So the second term, so this is the boundary of z. So it's just a pair of points. So pair of points with appropriate signs, so a plus point and a minus point. And then, so this entire thing is, I should be looking at gradient trajectories which start at P and on their way to some other critical point pass either through the plus point or through the minus point. There are actually no trajectories that pass through the plus point, but there is a single trajectory that passes through a minus point and then it lands at S. So second bracket is negative S. And this last term is actually 0 because the moduli space of gradient trajectories starting at P and passing through my chain, there's actually an entire one-dimensional space of those. So there's a one-dimensional moduli space of trajectories here. So the corresponding, so okay, that means that we assign 0 to this operation. So we have S minus S is 0. Okay, so this is just an example of a A-infinity relation. All right, so now kind of another example or related example. So let's say that again, we are considering two functions, f1 and f2 on some manifold, not necessarily a sphere. And let's say that we also have a collection of cycles on this manifold. Let's enumerate all the critical points of the difference of the two functions. Let's call them PIs. Then we can look at the following compositions. So I take a critical point PI, and I want the destination critical point to be PJ, and I'm interested in compositions of PI with a bunch of cycles, C alpha 1, C alpha 2, and so on, C alpha k, thought of as morphisms from F2 to F2. So then the corresponding, so then what we are doing, we are counting gradient trajectories starting at PI, ending at PJ, and passing through the collection of cycles. And I can form a generating function for all such compositions, multiplying those numbers by appropriate generating parameters, T alpha 1 through T alpha k. And they should be, well, even or odd, depend, well, the parity is opposite to the codimension of the cycle. You can actually assign some z degree, if you like, to them. Okay, so then this generating function is some kind of t-dependent matrix, and I can use it to it actually gives me a deformation of the Morse differential. So if I add to the Morse differential this matrix, so I'm thinking of the Morse differential itself as a matrix, well, of the size, which is the number of critical points. So, well, then I have this kind of deformed differential acting on Morse chains while I join all the generating parameters. And, well, it actually does square to 0, and you can see it either as a consequence of the A-infinity relations, or you can prove it independently by homological perturbation lemma. So for that, you should think of the differential forms on my manifold with the Ram differential. And that's kind of the big complex. And the small complex is the Morse chains. So actually, if we are kind of trying to be more precise, then they should be Morse, maybe I should say co-chains, or kind of Morse chains, but with cohomological grading by Morse co-index. And so equipped with Morse differential. So then the Morse chains actually can be realized as a deformation retract of the Ram complex. And there's a way to include Morse chains upstairs to project from differential forms to the Morse chains. And there's a chain homotopy operator.
Pasha, sorry, so you're now having some kind of Durham currents, right? Upstairs.
Yes. Yes.
So can you replace them by some whatever smooth representatives, or is it essential to have those? I don't know, to have those.
Yeah, so this is sort of a tricky question that I wanted to gloss over. So, but it is kind of an essential question, really. So I wanted to present kind of the naive model for this for this IP and K, which sort of lend. So the inclusion, for instance, will land in actually in the RAM currents, but then you can you can actually correct it or regularize this picture to land in smooth forms. And I think there are different ways to do it. One way is explained in Conservation Soberman paper. So there's a way just to regularize this triple.
Okay, but we agree that now as written, right, you need to do something with it, because in particular you want to square that operator and like.
Yes.
Okay.
Yes. So here actually, yeah, so if you take the collection of cycles, which is transversal, then you will not have a problem here, at least naively, because whenever you're trying to, so there will be no problem with sort of self-intersection of cycles because of the generating parameters. So they will be odd whenever you are considering some, you'll have a square of an odd generating parameter.
Okay.
Mm-hmm. But no, you're absolutely right. So things have to be regularized to be more precise. Okay. Yes. So, all right. Yes, so we have a deformation of the Durham operator upstairs by some kind of, well, okay, deformation of the differential. So let me call the kind of the Durham D1 and this by D2. So a deformation of the differential. So it is a version of what's called Novikov deformation of the differential by one form. So, well, here it would be a Novikov case if the codimensions of cycles are 1. Here we don't have necessarily them to be 1. And then we can calculate the induced differential and the induced or the induced perturbation of the Morse differential by homological perturbation lemma. It will be given by some formula that, okay, you should kind of go from the small complex to the big complex, then do D2 and then return. Or you should also go to the big complex, do D2, do K, do D2 and then return. And then, well, return with 2Ks, return with 3Ks and so on. So it's a geometric progression formula. So this formula actually literally leads back to this to this formula for M. If if we use the correct IPK triple. All right, so and that's also an argument why the differential downstairs squares to 0. That's just a feature of, well, it's part of the statements of homological perturbation lemma. Okay, now about this IP and K triple. So I present here this sort of naive, non-regularized version. So kind of the picture that we would like. So the wishful picture. So the inclusion. So critical points downstairs. So again, what we are doing is we are including Morse chains into differential forms on X. So critical points are included as delta forms on the unstable manifolds. So I have a critical point, I have the unstable or descending manifold of that critical point. So I want a delta form on that unstable manifold. So, okay, projection. I take a differential form on X, and the projection will be a sum over critical points. And the coefficient of each critical point would be an integration of my input form over the stable manifold or ascending manifold of that critical point. And the chain contraction is, okay, I want to write it in this way, so it will be useful for us later. So as an integral over some auxiliary parameter, which is, well, physically it's the proper time parameter. So it is a map from differential forms on X to differential forms 1 degree lower. And in this formula, V is the gradient vector field of my Morse function F. So, okay, so this is the pullback by the flow, by the gradient flow in time t. So another way to understand this operator is that it's an integral operator with a distributional kernel, which is, okay, some, this distributional kernel is a delta form of certain submanifold of X cross X. And this submanifold consists of all pairs, X comma Y, such that X is a gradient flow applied to Y in some t. Right? So I can flow from Y to X in some positive time. Okay, but well, if one is more precise, then these maps should be regularized, especially the map I. But well, let me just say that this is possible to do. Okay, so now the first picture, so I promised that it will be effective action, but first sort of pre-effective action, the more mathematical viewpoint of what's going on is homotopy transfer. So from a certain big differential graded algebra to some small algebra. So the big algebra is differential forms on X tensored with matrices of size n by n. So rows and columns in the matrix correspond to, well, objects. So kind of an entry in the matrix is characterized by a row and a column. So we are thinking about well, an entry corresponding to morphisms from A to B. So in other words, the object upstairs is okay, just a sum of n squared copies of differential forms bicolored by AB. Okay, so this is a differential graded algebra with just the RAM product of forms. So well, I have this product with the appropriate selection rules for indices. And the differential is just the de Rham differential. So now I want to contract this algebra structure, this DG algebra structure, to kind of something smaller, and this something smaller is the following. So it is a complex where kind of the diagonal component, so it's again split into MAB, so M for Morse. So the diagonal components are just differential forms, just copies of the space of differential forms, and off-diagonal components are Morse chains of the difference FA minus FB. Okay, so we are doing this kind of contraction of, okay, we are having, okay, differential forms kind of written in a matrix, and we are not doing anything with the diagonal differential forms, but for off-diagonal forms, we are doing the Morse contraction for the off-diagonal ones. Morse contraction corresponding to FA minus FB, where this A and B are kind of the row in the column. So this is what is written here. So our contraction data, well, the inclusion and projection in the chain homotopy are, well, the Morse contraction for off-diagonal terms and, well, trivial contraction or no contraction happening for A equal to B for the diagonal terms. So the induced algebra structure is given by sum over trees formula. So which is, I think, also formula from Kancerich-Soberman paper, and it's a completely general formula how to induce an A-infinity structure, A-infinity algebra structure on a deformation retract of a DG algebra or another A-infinity algebra. So here we have the higher multiplications that are given by some as sums of trees. So these are just combinatorial trees, binary rooted trees, where we put the inputs on the leaves included into the big complex. Then at each edge, we do the product in the algebra upstairs. On each internal edge, so in each vertex, we do the product in the big algebra. On each edge, we do the chain contraction. And finally, so we read it off as an operation flowing from, sort of going from leaves to the root. And when we reach the root, we do the projection to the small complex. So here, well, we are applying it to our example. So again, xi's, they, well, are elements of the corresponding pieces of this complex M. So we imagine that we have again a collection of indices. So A1, A2, dot, 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 dot. And well, X1 is a morphism from A1 to A2, that is either a critical point or a chain if the indices coincide. Then we have X2 and so on. So we plug those inputs on the leaves and we read off what goes in the output. And well, this gives us the A-infinity structure, and sort of plugging in our formulas for the for I, P, and K, we realize that we get exactly the composition maps from the Fukaya-Morse category. Okay, so on the inputs here we have either Morse chains or forms, but for forms we can take delta forms on singular chains. Okay, so kind of the physicsy interpretation of what's going on is that we want to have a look at the following topological gauge theory. So it's called BF theory on X, on the manifold X. So it's a gauge theory in Bataillon-Vilkavisky formalism. So the fields are non-homogeneous differential forms on X with coefficients in n by n matrices. So roughly speaking, so I want to kind of, so there is some correction to this picture, which is this extra factor A. So, okay, so the field A is a differential form with coefficients in n by n matrices. The form B is also non-homogeneous differential form, also with coefficients in n by n matrices. So there is some kind of correction to this picture. So somehow the physics picture or the gauge theory cares about L-infinity structures rather than A-infinity. So if I literally did what I'm saying, then we would have forgotten the A-infinity story, and we would remember only its symmetrized part, sort of only the L-infinity shadow of the A-infinity story. So in order not to forget the A-infinity story, I need to inject extra non-commutativity in the game. And it's, yes, please.
Just a question, and the Fukaya category, what would it correspond to if you forget A-infinity and go to L-infinity?
Right. So one thing that I think does not exist is an L-infinity category. So I think you cannot symmetrize a category, but you can symmetrize the corresponding algebra. So you can symmetrize the kind of the algebra the A-infinity algebra corresponding to A-infinity category. You can symmetrize it and obtain an L-infinity algebra.
Okay.
So and then it is just okay for forgetting some part of the information. Essentially, what it forgets is, well, for instance, it would forget in this picture, I should be, for instance, remembering the order in which I'm passing through cycles. In the symmetrized picture, I will forget that order.
Okay. Mm-hmm. Thank you.
So yeah, I'm sorry. I'm maybe kind of. I'm trying trying to find the words how to say it. And actually, this story of generating function that I told here, it was actually secretly a symmetrized story because we put here the generating parameters which were super commutative.
Oh, wait. So this slide was just misleading or what?
No, it is not misleading, but okay, the word generating function usually means that you remember all the data. Here we remembered actually some symmetrized part of the data of compositions.
But then, but what I mean, the transfer that you described.
Yes.
This is not a real transfer that you're doing, right? Because you need to, I guess you need to do the transfer of everything, not only of that symmetrized information.
Okay, so the transfer is on the A-infinity level. We remember everything here.
So that's the true, or whatever, the glimpse into a true picture of the transfer. That's this slide.
Yes. This is the full picture. So there's we're not forgetting anything here.
Okay, thank you.
It's when we want to encode it in a gauge theory, then sort of gauge theory cares about L-infinity structures, and if we want our gauge fields to be literally the elements of this complex, then we would be in trouble because it would only care about the DG algebra associated to this associative algebra. So we would be forgetting something. Okay, and the way not to forget something is to kind of have our fields being matrices or differential forms with values in n by n matrices, but entries of those matrices themselves, they should take values in some non-commutative place. And let me take this non-commutative place to be upper triangular matrices of size n twiddle by n twiddle. And again, n twiddle, something very large. So this n twiddle is related to how large of an arity of compositions we should be considering. So I should take n twiddle to be very large. Okay, so then the correct Lie algebra for the gauge theory, so the structure Lie algebra is matrices n by n tensored with upper triangular matrices viewed as a Lie algebra. So that is the correct picture from which we can recover back the A-infinity structure, which I'll mention in a second how to do it. So, okay, then it's just an ordinary sort of BF theory, written in BV formalism in the sense that I'm saying that, okay, fields here are non-homogeneous differential forms. So there are it's a mixture of everything: classical fields, ghosts, ghosts for ghosts and so on, and anti-fields, anti-ghosts and so on. They're all here. So this is kind of the EKS-Z way of thinking about BF theory. And here, okay, first let me say it in words, the idea, and then with some more formulas. So we want to calculate the effective action. So effective action on, okay, so I want to induce the effective action on sort of the diagonal components of fields. So we want essentially to integrate out the off-diagonal components of fields, but we will be integrating them out not completely, but up to some small remnant. And the small remnant is the Morse chains. So there will be certain kind of zero modes that we are not integrating out. And okay, so this is a gauge theory. For this process of integrating out, you need some gauge fixing, and this is the gauge fixing that we want. And so the gauge fixing is that for an off-diagonal kind of field component, we want its contraction with the gradient vector field to vanish. So this is a version of axial gauge, but sort of a tricky one. So we are imposing axial gauges pointing in different directions for different components of the field. So the name that Andrei Losev was proposing for this gauge fixing. So this gauge fixing is sort of our starting point. Essentially here, it's at the heart of the matter. And he proposed the name Coulomb-Nekrasov gauge because, well, they discussed with Nikita Nekrasov, it appeared in some discussion. So anyways, it's an axial gauge, but sort of pointing in different directions for different field components. Okay. So, well, slightly more explicitly, what we are doing is, okay, we have a big space of fields, so all those non-homogeneous differential forms with values and matrices, and we want to kind of push forward or kind of collapse to some small space, which is, I don't know, slow fields or infrared fields, in kind of terminology of Wilson's RG flow. And this small space is, well, essentially my complex M from before, but, well, tensored with this algebra A, which injects this appropriate non-commutativity in the game. And, well, this only takes care of the A field, of the kind of slow part of the A field, and then I need to add the dual, which corresponds to the slow B field. So then, okay, we can split the space of fields into slow fields and fast fields, and, well, you can glean what are the fast fields from this Morse chain contraction data. So there's kind of, okay, slow fields and fast fields, and we want to integrate over the fast fields. Well, actually, since this is Batarin-Vilkarisky setting, you need to integrate over a Lagrangian inside the fast field. So this is a splitting compatible with odd symplectic structure, and we need to choose a Lagrangian here. And Lagrangian is constructed out of the chain contraction. So, and, well, the picture is that, well, the picture of a BV push forward or BV fiber integral. So you have this big space of fields, which is sort of souped up, well, matrix valued differential forms. it's fibered over slow fields. And the fibers are, I'll put in some random colors here. The fibers are translates of this F double prime of the fast fields. And inside, well, completely random colors. Okay, so inside this fiber, I have the Lagrangian, and I want to integrate over this Lagrangian. Oh, what happened? Okay, I want to integrate over this Lagrangian, and I want to move this fiber around along F prime. So as I move it, I obtain a function on F prime. So integration over the Lagrangian, but depending on the point on F prime gives me this, well, exponential of the effective action. Right? So I can calculate it by perturbation theory in terms of Feynman diagrams, and these are the Feynman diagrams that I'm getting. Actually, I get only trees here, only trees, nothing else. And well, yes, please.
Pavel, sorry, just a quick question. There in the exponent, why don't you have the curvature term of the action that is in the previous slide?
The curvature term?
So the BF action has also, well, the A bracket A.
Oh, yes, yes. Oh, sorry. There's a typo in this slide. Sorry.
Okay.
Does this answer the question? I'm very sorry.
Yeah.
I missed
okay, thank you. Yeah. That's
Right. So the cubic term, of course, corresponds to the cubic vertices in the diagram. Right. So the curvature term is, of course, key in the sense that, okay, the action contains the kinetic term, which is responsible for propagators, for the edges, and the cubic term, which is responsible for the vertices.
Right. Thank you.
Yeah. Sorry. Thanks for setting me straight here. Yeah. Okay. So so we get an effective action which depends on this sort of slow fields, and the slow fields are diagonal differential forms and off-diagonal critical points. So we put on so this is a sum over kind of trees without the ribbon structure, or non-planar trees, which is again a shadow of this Lie versus A-infinity story. So okay, so actually they should come with 1 over the number of automorphisms, to be frank, 1 over the number of automorphisms. So okay, so each tree corresponds to some kind of monomial in A primes and, well, linear in B prime. So, and you calculate this monomial essentially by putting the kind of inclusion of A prime on all the leaves, calculating the bracket in the big DG Lie algebra. So here, well, this without achieved by 1 is a differential graded Lie algebra. So I'm calculating the corresponding bracket, which is essentially the Lie bracket of matrices tensored with Lie bracket in the Lie algebra G tensored with wedge product of forms. Okay, so I'm putting that kind of bracket in each vertex, and I'm putting my chain contraction, which now plays the role of a propagator from the standpoint of field theory at each edge. Okay, so this is the formula. And you can also think of kind of split this formula into terms according to how many leaves does a tree have. So that's the power in the A prime field. So you can write this formula in this form. So a sum over n's, well, B prime paired with some polylinear operation applied to several copies of A prime. So you can read off this polylinear skew symmetric operations. They are L-infinity operations induced on this M tensored with this algebra of upper triangular matrices A. So the fact that this is an L-infinity algebra corresponds in sort of in this physics language to the fact that the induced action satisfies the Bataillon-Vilkarisky master equation. So this is the only place where I can pronounce Poisson here, because this is an odd Poisson bracket. So okay, so this is the Bataillon-Vilkarisky master equation. So well, it's both classical and quantum master equation. It's both. There is no quantum term here. So master equation.
Is this actually a Gerstenhaber bracket?
It is yes, that's correct, because it's an odd Poisson structure. Absolutely, yes, it's a Gerstenhaber bracket. Yes, so Poisson by abuse of language. So Poisson of degree +1 corresponding to this symplectic structure here, odd symplectic structure again. Okay, so this L-infinity property of these polylinear operations correspond, so they're generated by this equation. Okay, so maybe one comment here. Yeah, and well, the mass equation is something that, well, formally follows from, well, Stokes' theorem for BV integrals. Less formally, you need to prove it on the level of Feynman diagrams, and then it essentially becomes the same argument as in Kanseri-Söderman formula. So you need to, you can formulate the argument on the level of Feynman diagrams. Why this relation holds. Okay, now just a little comment. About recovering the A-infinity operations. Well, that's why we needed this extra algebra A. Is, well, let's take T12 to be the upper triangular matrix with, well, only 1, 2 entry, and all the other entries 0, and, well, similarly T23 and so on. So I take a bunch of elements from M and tensor it with corresponding upper triangular matrices. Then the L-infinity operation applied to these inputs is proportional to kind of upper triangular matrix which has a unit here and zeros everywhere else. Sorry, okay, somewhere has a unit at the place 1 and +1. And zeros everywhere else, and the coefficient is the A-infinity operation. So we can read off the A-infinity operations on M. We are not losing any information. So that was the whole reason to put this extra coefficient algebra. Okay, so that was picture 1. Now picture 2, or first quantization picture. So the previous was a second quantization picture. So picture 2 is the following. It's so topological quantum mechanics, or higher topological quantum mechanics in Andrei's favorite terminology. So sort of the inspiration here comes from, I would say, from topological string theory, where sort of one produces the answer of a field theory is a differential form, non-homogeneous differential form on the moduli space, well, MGN, on the moduli space of curves, with values somewhere in some kind of operators with some inputs and some output corresponding to punctures. And, well, this differential form is supposed to have some properties. So it should be BRST closed and have some factorization property on the boundary of the compactified moduli space. And from periods of this form, you are getting some interesting relations like WDVV equation. So here it's essentially a similar story, but one-dimensional law. Instead of moduli space of curves, you have a moduli space of metric trees. So first, topological quantum mechanics before the trees. So we have a collection of particles of colors A, B, or maybe I should draw A on one side and B on the other side, with A different from B. So the space of states for such a particle will be just a copy of differential forms on X. The BRST operator is just the de Rham operator. And the Hamiltonian is, okay, it's the Lie derivative along the gradient vector field of Fa minus Fb. So it's a gradient vector field of Fa minus Fb. So the Hamiltonian is the Lie derivative. So it's sometimes called Morse quantum mechanics. So it can be written, this Hamiltonian, as an anticommutator of the BRST differential with something. So, and this something is the contraction with the gradient vector field. So, okay, so this is kind of a particular a limit of the supersymmetric n equal to supersymmetric quantum mechanics that was considered by Witten in 1982. So yeah, so you can recognize this. So some linear combinations of this Q and G, so sum and difference, as generators of n equal 2 supersymmetry algebra. So it's essentially, you can call it either topological quantum mechanics or in n equal 2 supersymmetric. So the evolution operator for an interval of length t is the following. So it's e to the negative t times the Hamiltonian, as usual in quantum mechanics. But actually, I want to consider the evolution operator as dependent on t comma dt. So it's actually a non-homogeneous differential form on the moduli space of metric intervals. So I can write it as e to the negative th 1 minus dt times g. So it has a kind of 0 form component and 1 form component. So it's a differential form on the space of metric intervals. So this is the length of the interval. And well, valued in operators on the Hilbert space. All right. So now let's proceed to the topological quantum mechanics on trees. So now instead of just intervals, I have trees where I can have tree-valent vertex like that, where the colorings of the edges should match correctly, right? Like here. So an AB particle can collide with a BC particle and then will produce an AC particle. And the corresponding operator on the spaces of states is just wedge product of differential forms. Now I can also have a bivalent vertex, which can occur on to an AB particle. We can have kind of an operator colored by some chain, and the operator is just wedging with the delta form of that chain. And well, okay, it also has some color, either A or B. So we also have univalent vertices, which corresponds to, well, states, or in states. And a univalent vertex is decorated by a critical point of Fa minus Fb, and the state is just this delta form of the unstable manifold. Now we also have edges in our graphs, and the edges are assigned this, this evolution operator or super propagator that I wrote on the previous slide. So this one. All right, but sort of corresponding to the function Fa minus Fb. So it depends on the on this bicolor of an edge. Now, okay, now the output of the topological quantum mechanics is, well, obtained by combining all those objects for all the elements of your picture. And it is a differential form on the moduli space of metric trees with n colors involved. So in other words, you have n minus 1, let me see, n minus 1 leaves in the game, n minus 1 leaves. So and with, so we're considering metric trees with okay, n minus leaves and the root, and with k1 binary vertices of color 1, so they occur on the sort of on the border of the ribbon graph colored with 1, with k2 binary vertices colored with 2, so they occur on this second border, k3 vertices of color 3, and so on. Okay, so our output is a differential form on the space of trees, which is some cube complex, because, well, we have lengths here between different vertices. And well, it's valued in some well, home space, so it eats the decorations of unary vertices, which are critical points, and it eats the decorations of binary vertices, which are chains, which are chains. Okay, and produces some well, linear combination of critical points at the root. So hence the output. Okay, so here's a picture of some of the top degree cells of this moduli space of metric trees with 4 colors, a single binary vertex of color 1, single binary vertex of color 2, and no binary vertices of colors 2 and 3. So here, for instance, we can have, well, this graph. So blue is color 1, red is color 2, green is color 3, and brown is color 4. So we have a single blue vertex and single red vertex. But then we can also like do a kind of a move on these two vertices like that, and that would still be in the same moduli space. And we can also slide around the green, red and blue vertices on the corresponding borders. Right? So this whole moduli space is some sort of a cube complex, and the dimension here is dimensions of this cubical cells is 3, because there are 3 time parameters, and I'm thinking of well, edges attached to the boundaries attached to the univariant vertices as having length infinity plus infinity. Okay, so now here's an example of the value of the topological quantum mechanics on, let's say, this particular picture, which was the middle picture here. Okay, so I'm putting as an input 3 critical points and 2 chains. So the result will be a sum of a critical point, well, sitting here of f1 minus f4 with some coefficients, and the coefficient is a differential form on, well, depending on these 3 lengths. And here is the differential form. You just read it off from the graph, right? So you read it off. Okay, so here I'm plugging in, well, the in state, which is delta of the unstable manifold of P12. Then I am sort of encountering this operator of wedging with the delta form of a chain. So I'm here. Then I'm evolving in time t. So I'm evolving in time t using the topological quantum mechanics for f1 minus f2. Okay, so I arrived here. Now I need to take care of this part of the graph. So in a similar way. So at this point, I'm using the wedge product because this is a trivalent vertex with compatible decorations. So this is the wedge product that I'm doing. Then I'm here, and now I'm evolving in time t double prime. So I have evolved. Now I'm here. Now I need to wedge with the in state coming from here. So, oh, actually that should be unstable of P34. Sorry, a typo. Unstable of P34. So then I'm here, and now I just need to pair it with the out state corresponding to the root, which is this operation integration against delta form on the stable manifold of P14. Okay, so this is a differential form depending on 3 lengths. So how does okay, why A-infinity property works here? So it follows from 3 properties. One property is that the de Rham operator on length, so the de Rham operator on the space of metric trees, plus the BRST operator annihilates I. So Q acts by, well, D Morse or the boundary operator on the inputs, on the morphism spaces here. So that's how Q acts. So I have D Morse, sorry, I have de Rham on metric trees acting on this factor, and I have Q acting on all these factors. Okay, so the next property is the factorization on the infrared boundary of the moduli space of trees. So infrared boundary is the situation when one of the lengths becomes infinitely large. So in that situation, my tree splits into 2 subtrees, T1 and T2, and I should just wedge the corresponding differential forms in the differential form part and take the composition or just plug the output of one tree as the input for another in the sort of in the coefficient part. And finally, the period is that if I take the integral of my differential form I over the entire space of metric trees, so take the biggest period, then it gives me the composition map of the Fukaya-Morse category. So again, I'm looking here. So I'm integrating, sort of I'm killing this first factor by taking the integral over the moduli space of trees. I'm getting something here, which is exactly a composition in the Fukaya-Morse category. Okay, so and how does one, knowing that, how does one prove the A-infinity relations? So one looks at this closedness property and just integrates both sides over the moduli space of metric trees. So on one side you have Q times the Q applied to the integral of I over the metric trees, which is Q applied to the composition in the Fukaya-Morse category, which is responsible for a part of terms in the A-infinity relation, namely responsible for those terms where the inner M acts on a single input that takes care of those terms. And then the other side is the integral by Stokes theorem. On the moduli space of metric trees. We should be integrating over the boundary of the space of metric trees of my differential form I. And here one needs to analyze the boundary. And there are different sort of different pieces of the boundary. So there are ultraviolet pieces where some length of some edge goes to 0, and most of those pieces, they just cancel out for different situations when you take into account different graphs or kind of the adjacency of different cells, different cubical cells in your complex. There is one kind of boundary which does not cancel out, and that's when you have two binary vertices of the same color colliding. They do not cancel out, and they lead to the special kind of terms in an A-infinity relation when you have inner composition applied to a pair of chains. And finally, there is the infrared boundary, which corresponds to one length becoming infinitely big, and then what we get is essentially all the other terms in the A-infinity relation, where the inner M is involving two or more colors. And well, that is everything that I wanted to tell you. So yeah, that's the story. So thank you very much. I'm sorry I'm a little bit out of time.
So do we have any questions?
Thank you. Nice talk. It's just about pretty formal stuff. If you consider like AKZ model with a polynomial target, instead of cubic action, you get more other graphs, but still more or less you get the same thing with other graph. You get kind of form some graphs, labeled by something.
Right. So I'm not sure I fully understood the question. So here we took upstairs the usual one with only the cubic vertex, but kind of formally, you can consider BF. Consider BF for some L-infinity algebra.
I see. Yeah. Okay.
Absolutely.
Okay.
There's a question from Alejandro.
Yes. Thank you for the talk. I wanted to ask you. It might be an esoteric question, but is this? Can you get all these things from some sort of master field theory? Even this trick using the upper triangular matrices.
So I'm not sure what you mean by master field theory. So in some sense, BF theory is here the master field theory.
Right, but it has these coefficients, maybe unusual coefficients.
Yes, so somehow I needed a trick to non-commutivize the original space to encode sort of the A-infinity story that I wanted in an L-infinity story. So somehow there is some philosophical point which I'm I'm not sure that I can elaborate on well enough, that somehow this physics story cares about Lie version of objects.
Right, but
we need to encode the infinity inside L-infinity, and for that we needed these coefficients.
Right.
We can take just some kind of some whatever direct limit and of this upper triangular matrices. Actually, I put upper triangular here so that we don't have one loop graphs, because we could put square matrices of large size, for instance, and then it's actually also interesting. Then you would also produce one loop graphs in the story. I'm not quite sure what they mean. They correspond to homotopy transfer of some kind of more subtle object, I guess, not maybe A-infinity algebra, but sort of A-infinity, whatever, quantum A-infinity.
And can you interpret this algebra A as also coming from some other maybe auxiliary field theory construction?
No, I don't know how to do that. For me, it's a gadget that I need to write down the field theory, essentially.
I see. I was thinking more about something like adding one more dimension or something like this, but
that would be very clever. But I don't know how to understand that.
Okay, thank you.
Thank you. That's an interesting thought.
And I see Anton has another question.
Yeah, sorry for asking many questions. So I have a somewhat provocative question. How is it? Do I understand correctly that this BF theory, it is more or less the same as the original A-infinity? So that's just a little bit of a packaging.
Yes.
And
yes.
But what about Morse quantum mechanics? That at least looks somewhat different. That you have more stuff in there. Could you comment? Is it also a packaging, or there is some like what is the extra structure? What's is there more information when you do this homological quantum mechanics, or?
No, I think it's also a packaging. I don't think that there's more information. It's just a different style of packaging. But I mean, these packagings, they're sort of, they maybe are supposed to talk to, I don't know, different parts of your brain. So one is a kind of packaging where everything is about a gauge theory, and the other packaging is where everything is about essentially something like WDV equation. So they're different metaphors.
Well, okay, that sounds poetic. But,
yes, but yes, I can.
But maybe more concretely, for instance, in this topological quantum mechanics, you explained to us this Stokes formula, right?
Yes.
So what is this Stokes formula, for instance? Does it directly translate in gauge theory to something, or kind of, right, these technical tools, would they also be one-to-one, or for instance, this Stokes formula will be only in topological quantum mechanics picture?
So that is actually a good question, and so this is sort of a little bit of, well, I don't know, hope that I had, but yeah, I don't know if it will work out or not. So right, so there is kind of a Stokes argument, like in that is used to prove mass equations. So Stokes argument on the configuration space of points, which was used in like Axel Rotzinger papers on Chern-Simons theory, and in Maxim Kontsevich's paper on Poisson on deformation quantization, for instance. So there is this Stokes argument, which essentially allows you to prove the mass equation, but it works for propagators of special types. So for nice propagators that corresponds to differential forms that lift to the compactified space of configuration, compactified configuration space of points. So of Hodge type, like the integral kernel of d star divided by the Laplacian. So the propagator that, oh, what happened? The propagator that we use here is much more singular. So it's the axial gauge propagator. So this propagator has the property that answers are much more computable here. So they correspond to a counting problem, to an enumerative problem. But running this sort of argument with the Stokes theorem on the configuration space of points doesn't work because, okay, you don't have a smooth differential form on the compactified configuration space of points. But on the other hand, here we have another kind of Stokes theorem argument on a different space, not on the configuration space of points, but on the moduli space of trees. So, and therein sort of lays sort of a vague hope that maybe you can be able to prove, I don't know, mass equation for, I don't know, effective action computed, this singular but very computable gauge, let's say in Chern-Simons, or it's also very lucrative to use this sort of computable but singular gauge. Maybe it can be proved using this trick. So using this different moduli space and its boundary. So it's a long answer, but yeah.
Yeah, thanks a lot. It's a very useful long answer.
Mm-hmm.
Yeah, I have kind of short question about your choice of additional cycles. From the point of view of Fukaya categories, can I think of them as a choice of what they call bounding chain or cochain for the corresponding graphs of the functions for the corresponding Lagrangians?
So they would correspond. Let me just roll back to the picture. They would correspond to like asking, let's see, let me zoom in. Okay, I want to have, let's say, like a red chain here on L2, and I would be asking about Morse. I would be asking about holomorphic disks with the condition that this part of the boundary passes through this chain.
I think this bounding chain they used for a similar purpose, if I'm not mistaken.
Mm-hmm.
Yes, at least it resembles.
Right. So here, thank you for the comment. I'm not educated in Fukaya category, and I have to say so. I know that there are different.
Nobody is.
Mm-hmm.
Okay, thank you.
Mm-hmm.
Okay, any other questions? No, then I would say let's thank the speaker again. Thanks, Pavel.
Thank you so much. Thank you.
And our speaker next week, I believe, is going to be Kai Behrendt. Is that right? Yeah.